Volcanoes are hot. They spew molten rock and ash into the atmosphere, and their eruptions can block out the sun. With all of that heat and matter in the air, you'd think they might be good at keeping our planet warm. But depending on where they're located and what kind of magma they're made of, volcanoes can actually cool the planet down. So it's no surprise that scientists are studying them as part of their search for solutions to climate change. There's just one problem. People have been messing with volcanoes for thousands of years, which makes it hard to know how natural processes work without us getting in the way. But there is hope. We have plenty of historical records of major eruptions, and scientists are learning more about what those events were like. And by studying these past eruptions, researchers are better understanding how volcanoes affect the climate and how we might be able to harness that power for good. One of the biggest recent eruptions was the 1815 eruption of Mount Tambora in Indonesia. This volcano blew its top so hard that it left a crater 2.5 kilometers wide and 3 kilometers deep. That blast sent over 51 billion cubic meters of ash and rock into the atmosphere. Ash fell as far away as Australia, more than 3,000 kilometers from Tambora. The eruption was so massive that the year 1816 became known as the year without a summer. The northern hemisphere experienced unusually cold temperatures, and there were widespread crop failures across Europe and North America. And sadly, some people took this literally. As in some places, people started celebrating the end of the world. It was not great. But other big eruptions had the opposite effect, making the planet warmer. For example, in the 1990s, researchers noticed that after the 1983 eruption of Chichón in Mexico, the average global temperature went up by about half a degree. Now, while that might sound like a small amount, it's comparable to the warming we've seen in the last few decades. And Chichón didn't even send that much material into the air. Its eruption was about 10 times smaller than Tambora's. So why did it have such a big impact? Well, it turns out that what you put into the atmosphere matters just as much as how much you put in. See, when a volcano erupts, it releases sulfur dioxide gas along with everything else. Sulfur dioxide is great at reflecting sunlight, which is why you should never look directly at one, because your eyes are basically little suns. And if enough sulfur dioxide makes it into the atmosphere, it can form a layer of clouds high above the Earth that reflect a lot of incoming sunlight back into space. This cools the planet. But if it sinks down into the lower atmosphere, it can also form sulfuric acid, which forms aerosols that linger in the air for months or even years. These aerosols absorb and re-emit energy from the sun, heating the atmosphere. So the type of volcanic eruption that warms the planet is the one that doesn't make it rain, which sounds pretty counterintuitive. After all, we know that rain can cause global warming because water vapor is a greenhouse gas. And when water condenses into clouds, it releases heat. But rain also removes water vapor from the atmosphere. And water vapor is actually the most abundant greenhouse gas in the atmosphere. So removing it, even if it falls back down to Earth as rain, can have a net cooling effect. And here's where things get complicated. When an eruption takes place underwater or near a body of water, it can form a huge cloud of steam, which is mostly water vapor. And water vapor is really good at trapping heat. This means that some volcanic eruptions, especially underwater ones, may cause global warming, but they only affect a thin layer of the atmosphere right above the eruption site. On the other hand, when steam from an eruption rises into the stratosphere, which is the second layer of the atmosphere, it can help form polar stratospheric clouds. These clouds can then catalyze the destruction of ozone, leading to a hole in the ozone layer. Meanwhile, up in the mesosphere, another atmospheric layer above the stratosphere, volcanic eruptions may actually help keep the atmosphere stable, because volcanic particles in this layer form a thin insulating layer that protects the mesosphere from the sun's energy, keeping it from getting too hot and causing a runaway greenhouse effect. But while all these factors are important, they aren't the whole story. Just how much and how long the temperature varies after a volcanic eruption depends on lots of different factors, like how cold or warm the ocean is, how strong the winds are in different layers of the atmosphere, and how well mixed the atmosphere is. All of that means that even though we've identified which types of eruptions tend to cause warming or cooling, it's still really hard to predict how any individual eruption will affect the climate. But that doesn't mean we're not trying. One way researchers are improving their predictive models is by recreating volcanic eruptions in the lab. For example, scientists at the Smithsonian's Global Volcanism program built a device that uses compressed gas to simulate explosive volcanic activity. Using this machine, they've studied how bubbles form in magma, which affects how dangerous an eruption might be. And another team at the University of Liverpool used a combination of lasers and high-speed cameras to measure the movement of volcanic ash plumes under different conditions. But studying real-life eruptions is a lot more straightforward. In 2017, researchers looked at ice cores from Mount Pinatubo in the Philippines, which erupted in 1991. By measuring the concentrations of different elements, they found that although the eruption released about 5 million tons of sulfur dioxide, the real impact came from the 20 billion tons of carbon dioxide that it put out. More recently, in 2021, scientists analyzed ice core samples from the 2010 eruption of Eyjafjallajökull in Iceland. That eruption only ejected 170 million cubic meters of ash, and yet caused widespread disruption to air traffic in Europe. Turns out, the reason for the shutdown was a combination of the ash, which damaged aircraft engines, and unexpectedly high levels of sulfur dioxide, which created a thick layer of sulfuric acid aerosols. These are just two examples of how useful real-world data can be. And that data doesn't just come from scientists. You can actually contribute to our understanding of volcanoes through citizen science projects like the Smithsonian's My View of Mountains initiative. All you need to do is take a picture of a volcano and upload it. Then scientists can use your photo to track changes in volcanic landscapes over time. The more data we have, the better equipped we'll be to understand and predict how volcanoes affect the climate. And that knowledge could help us tackle the big problem: human-caused climate change. Scientists are looking into whether we could trigger beneficial eruptions to offset our emissions. But triggering an eruption on purpose is tricky business. If you somehow manage to melt a big chunk of ice at the North Pole, you could potentially trigger a chain reaction that melts the rest of the ice sheet and raises sea levels worldwide. So we have to tread very carefully. Luckily, Mother Nature has already given us a hint. Geothermal plants harness the heat from deep within the earth to generate electricity. And geothermal systems in Iceland have seen increased activity after volcanic eruptions. Plus, the country hasn't experienced a major eruption in over 70 years. So maybe we can learn from Iceland's lead. Now, none of this is going to happen overnight. Even with all the data we could ever hope for, we probably wouldn't want to trigger an eruption until we have a really good idea of how it will affect the surrounding ecosystem. Eruptions can cause major shifts in local climates, wiping out native plants and animals and leaving behind a barren landscape that won't recover for hundreds of years. Plus, large eruptions can threaten nearby towns and cities, which is why some places try to prevent eruptions rather than encourage them. In Indonesia, authorities recently conducted a controlled detonation of Mount Semeru, an active stratovolcano. By blowing off some of the pressure, they hoped to prevent a more serious eruption later on. But the eruption they triggered lasted longer and produced more ash than expected, forcing thousands of people to evacuate. That's not great. So for now, our best bet is to keep tabs on volcanoes around the world, both monitoring active ones and looking for signs of unrest in dormant volcanoes. The United States has a volcano threat assessment program that does exactly that. They maintain a list of volcanoes that could pose a serious danger and regularly publish reports on the likelihood that these volcanoes will erupt. And when an eruption does occur, they issue timely warnings to the public and emergency services. You see, predicting how volcanoes will affect the global climate is complicated enough when we're talking about natural eruptions. But when human activities are involved, it becomes an even trickier problem. Geothermal plants can increase local seismic activity, potentially increasing the likelihood of an eruption. But they can also provide an early warning system because they don't usually produce the same gases as magma. This means they can alert scientists that there's magma moving toward the surface. No matter how we slice it, predicting how volcanic activity will affect our planet is a tough job. But thanks to technology, scientists are constantly refining their methods, and we're learning more about the hidden forces that shape our world. Thank you for watching this SCI show video.